this session. My name is Federico Capasso from Harvard University, and I have the pleasure to introduce to you first the first speaker, Professor Bob Boyd. He holds two appointments, one at University of Ottawa, the other at University of Rochester. Really needs no introduction. He had a very distinguished career, which is continued to this day. He actually was a student of Charlie Towns, a Nobel Prize winner and an inventor and co-inventor of the META and the laser. And he went to a very distinguished career, contribution in quantum optics, quantum electronics, more recently, metasurfaces and application to, as you will hear today, near epsilon zero materials. And he wrote two very good books. In fact, one is my favorite in nonlinear optics, because I tell my students, this is actually the only book that I really could understand and redo the calculation myself without overdoing all this business with the tensors and so forth. So great job, Bob. And I want to finally say he has had many recognition in his career, chiefly the Charles Harder Towns Prize of OSA, the Quantum Electronics Award of IEEE, and notably shared with Vlad Shalaev the Frank Isaacson Prize last year for optical effects in solid of the American Physical Society. So welcome, Bob, and we are excited to hear your talk.
So Federico, thank you very much for those kind words. I also want to thank the conference organizers for inviting me to give this plenary talk. So the announced title is How Light Behaves When the Refractive Index Vanishes. When I give a very similar talk to a technical audience, I say it's about physics and applications of epsilon near zero materials. And of course, this is the same idea, just expressed a little bit differently. Okay, so here's a brief outline of what the talk is going to be about. First of all, we're going to talk about the physics of near zero index materials and epsilon near zero materials. Now, of course, the refractive index is the square root of the dielectric permittivity epsilon. So these are very, very intimately related concepts. But when it's important to distinguish them, I will. We'll then talk about nonlinear optical properties of ENZ and NZI materials. We'll then talk about metamaterials for studying these effects. And we're going to end up with some applications of epsilon near zero and near zero index materials. Okay, I call this a spoiler alert. If I were giving the talk differently, I would introduce this thought only halfway through and let the tension build. But there's an obvious question. What is the relationship between epsilon near zero behavior and a strong nonlinear optical response? Well, here is an intuitive way of understanding it. There's a standard relationship between N2 and chi3. And if you've forgotten the definition of N2 and chi3, I have them here at the bottom of the slide for you. But the standard relationship between N2 and chi3 is shown here. And you can see that when the linear refractive index N0 becomes very small, N2 is going to become very large. And I like to think of chi3 as the fundamental property of a material, and N2 is how that nonlinear is going to show up in specific geometries. Okay, so let me motivate the talk to come. So the goal of this field is to produce a giant nonlinear response of epsilon near zero metastructures. First of all, why would we care about nonlinear response? Well, nonlinear optics has many important applications. I won't go through them all. Photonic devices, quantum states of light. I mean, I don't think there's any linear process that can produce a quantum state of light. And fundamental understanding of light-matter interactions. Now, that's why we want nonlinear optics. However, the nonlinear response is usually much weaker than the linear response. So going back decades, people have been looking for means to enhance the nonlinear response. They've looked at resonance interactions, atomic vapors, plasmonic systems, electromagnetically induced transparency, metamaterials. So the approach that I've taken in my own work is to use epsilon near zero materials and epsilon near zero metamaterials. So, okay, let's get right into some of the physics. So physics of near zero index and epsilon near zero materials. Let me remind you that the wavelength of light is given by the vacuum wavelength divided by the refractive index. So if the refractive index becomes very small, the wavelength becomes stretched. I remind you that the phase velocity of light is given by c over n. So again, as n becomes very small, the phase velocity approaches infinity. So what we have then is that the wave picks up no phase, no propagation phase in going from the input to the output port. Now, one way of understanding this is that for n approaching zero, the field, one way of understanding this is that for n approaching zero, the field oscillates in time, but not in space. And the oscillations are in phase everywhere. So this is entirely consistent with Maxwell's equations, but it's a limit of Maxwell's equations that we usually don't consider. The earliest work that I know of speculating about what happens if the refractive index vanishes is this paper by Brown in 1953. This was the proceedings of the IEEE. The name hadn't changed yet at the time that this paper was written. Okay, so let's talk some more about the physics of epsilon near zero materials. And perhaps most remarkably, radiative processes are modified in ENZ materials. And for example, the Einstein A coefficient, which of course is the inverse of the spontaneous emission lifetime. The A coefficient is given by its value in vacuum times the refractive index. So that means that we can control spontaneous emission by placing the quantum emitter inside of a dielectric. The Einstein B coefficient, that's the one that we use to get the stimulated emission rate. The B coefficient is equal to the vacuum B coefficient divided by n times the group index. And under epsilon near zero materials, this denominator is going to be very small, and we expect the optical gain to be very large. Now, what are some of the implications of this? Well, if we can inhibit spontaneous emission, we can build thresholdless lasers. And also, we expect superradiance effects to be pronounced in ENZ materials. Superradiance involves cooperative spontaneous emission, but since the phase is everywhere the same in an ENZ material, all the oscillators necessarily will be emitting in phase. Okay, now let's turn to geometrical optics, sort of our simplest understanding of how optics works. And we start with Snell's law in its usual form. And just by putting in the numbers n is equal to 0 and n is equal to 1, we see that light always leaves perpendicular to the surface of an ENZ material. Here, no matter what the angle of incidence is on this side, the light will always leave perpendicular to the surface. Now, but you just reverse the direction of the light rays, and you see that light can enter an ENZ material only at normal incidence. So if light is going from vacuum into a zero index material, this ray will experience total internal reflection. None of it will get into the material. The only way you can get light into the material is to come in normal to the surface. But then the question is, what happens? Any value of theta on this side will satisfy Snell's law. So to answer this, we had to do a wave equation analysis. And Orad Reshef did this work. And you see that these are the phase fronts of the light leaving the epsilon near zero material. So you see that, in fact, light is emitted in all directions. Oh, some more consequences. I call these funny lenses. Planar surface, no matter how the light gets into this material, it always leaves perpendicular to the surface. If you put a curvature on the surface, it means that the light will always come to a focus at this point. It allows you to build large area, single transverse mode surface emitting lasers. So let's say this is the facet of your semiconductor diode laser, and this length, L, is much greater than the vacuum wavelength. You might think you have to worry about becoming overmoded, but you don't, because if this is a zero index material, the phase is the same everywhere in the material, and you can emit into a single mode. And I'll make the obvious comment that there are no Fabry-Perot interference. You simply do not pick a phase shift as you go from this entrance window to this exiting window. Some other consequences are shown here. One of them is supercoupling of waveguides. So the idea is this: you have a region that is filled up with n equals 0 material. You put a metallic cladding on this material. You send light into this waveguide. The light will exit from this waveguide. I mean, there is no other place for the light to go except to exit in this direction here. Another is coupling between two distant waveguides. So here's an epsilon near 0 waveguide. Here's another one. Well, the light that leaves this waveguide due to its evanescent tail will couple into this waveguide, no matter how large the separation is between the two of them. And the last process I want to talk about is something that's quite remarkable. It's the automatic phase matching of nonlinear optical processes. So recall that phase matching means that we need delta K, the wave vector mismatch of the process to vanish. But since K is n omega over C, if n is equal to 0, the wave vector must vanish, and delta K then automatically vanishes. What this means is that usually we would think of a four-wave mixing process as a typical four-wave mixing process: two photons going in the forward direction, coupled to two photons going in roughly the same direction. But with a zero index material, you can have two photons going in the forward direction, coupling to one photon in the forward direction and one photon in the backward direction. Your first thought is that, but that doesn't conserve momentum. Well, but it conserves crystal momentum because each of these vectors really has zero length. So in a trivial sense, this process is occurs and is phase matched. So here's some of our work on this. We call this relaxed phase matching requirements in ENZ media. And well, we are studying four-wave mixing. Just a generalization I just showed you: two pump photons breaking up into a signal and an idler photon. And well, we find that the idler field is generated in both the forward and the backward direction. So we have the forward process here, the backward process here. And this is the data showing that we really do emit light into the backward direction as well as in the forward direction. Now, what is the significance of this? Well, here's what I think. Nonlinear optical processes that were previously believed to be too weak to be useful can be excited through use of ENZ materials. In nonlinear optics, we are always struggling with how to achieve the phase matching condition. It seems as if ENZ materials give us an automatic route to satisfy these phase matching relations. Okay, I call this some details from electromagnetic theory, but in fact, I'm just showing this so that I can define epsilon, the relative permittivity, and mu, the relative permeability. And then it's very easy to show from Maxwell's equations that the refractive index is the square root of epsilon times mu. This means that n is equal to 0 when either epsilon is equal to 0 or mu is equal to 0 or both epsilon and mu are equal to 0. Now, one might wonder why in the world am I going to such detail? And here's why. There's a problem getting light into a zero index material. Well, there's always reflection from the boundary between two different materials. And this reflectivity can be written in terms of the impedance. And the impedance is written in this way here. So just looking at these equations, we see that the reflectivity will be 100% if epsilon is equal to 0, unless mu is equal to 0 as well. So that is why people are trying to find EMNZ materials, epsilon and mu both near 0. Okay, so time is fleeting. Let's move on to the nonlinear optical properties of near zero index materials. And okay, this is just schematic. One application of nonlinear optics is for optical switching. Here's an input beam, here's an output beam, here's a control. And what we want to do is have the control determine whether the input is blocked or whether it passes. So how do we do this? We want to switch with fast switching times and a strong nonlinear response. So this is sort of the challenge of people working in this field. We want strong nonlinear response, but we also want the nonlinearity to be fast. So that's the challenge that we put up to ourselves. Now, I showed you this already, just remind you of this standard relationship between N2 and chi3. Okay, so how do we choose an epsilon near 0 material? And I mean this at the conceptual level, at least for present. Well, what about an electrical conductor? Well, all conductors display ENZ behavior at their plasma frequency. So I remind you of the Drude formula, and you can see by inspection that the real part of epsilon will vanish for a frequency that's equal to the plasma frequency divided by the square root of epsilon infinity. So this works well. In fact, much of the work that has been reported to date, it has made use of plasmonic effects. But what about electrical insulators or dielectrics? Well, dielectrics can show ENZ behavior at their phonon resonance. So this is very useful, but ionic crystals, their phonon resonances tend to be in the mid to far infrared. So this works at that spectral range. Now, with metamaterials, in concept at least, you can do whatever you want. You tell some clever person what optical properties you want, and they build it for you. However, the challenge for any material system is that we want low loss. And that means we want the imaginary part of epsilon to be small at the wavelength where the real part of epsilon is small. That is not impossible, but these two conditions usually do not go together. So that is the challenge that we have in choosing materials. In my work, we've chosen to use indium tin oxide. It gives a very, very strong nonlinear response, 100 times larger than those of previously reported materials. Indium tin oxide is a degenerate semiconductor, meaning it's so highly doped as to be metal-like. It thus has a large density of free electrons and a bulk plasma frequency corresponding to a wavelength of 1.24 microns. We found that its dielectric properties are well described by the Drude formula. And there's more in life than just indium tin oxide. The group of Vlad Chilayev, who's speaking next, with Boltaseva and Faccio and others, have been studying aluminum doped zinc oxide. And I guess I would say that the two materials complement one another. Okay, so this slide reviews 2 years of my professional life where we were starting to work on indium tin oxide. So first of all, well, we got a commercial sample of indium tin oxide using ellipsometry. We measured the real and imaginary parts of epsilon, and we found that the imaginary part, the real part vanishes at a wavelength of 1240 nanometers, the value I quoted before. We then did a Z-scan measurement, and the results of the Z-scan measurement are shown here. There's a very, very pronounced peak in the nonlinear response at the ENZ wavelength. We then measured the overall change in refractive index, and we found that the real part of the refractive index can change by 0.8, almost a unity change in the refractive index. And all of this is with a sub-picosecond response time. So, so that's the material that I have been pushing in my own research. Just maybe an issue of detail, but a very important one. We studied the angular dependence of the nonlinear optical response. Here is N2 plotted as a function of wavelength as we gradually increase the angle of incidence of the material. And you see that as we come in at steeper and steeper angles, we get a larger response. And that just follows from the usual boundary conditions at an interface. So coming in at an angle made a very, very big difference for our work. Now, let me ask again the conceptual question of why does epsilon near zero lead to large nonlinear response? Well, I've already talked about the form of N2, but just to state that in a more general form, let's say that the refractive index is a background value plus a small change delta n, and that epsilon has some background value plus some small change delta epsilon. Then we can express n as a function of the epsilon background and change, and we take this to first order. And what we find is that the change in the refractive index is equal to the change in dielectric permittivity divided by twice the background index. So once again, if the background index is very small, we get a large enhancement of the refractive index. Another way to understand this, in fact, I think these are just independent effects. Let's look at the wave equation. If epsilon or mu or both vanish, this term disappears entirely. Then the entire material response is given by this term involving the nonlinear polarization. So we're in a very different regime. We usually think that the nonlinear polarization is a perturbation on the linear response, but here there is no linear response. So this vanishes. So this is the only term. Okay, and finally, from Maxwell's equations, it is easy to show that the nonlinear response scales as the square root of mu over epsilon. Now, I say it's easy to show. Well, it was easy for Nader and Gaeta to show this, and I've been working with him on this project. And here is an example that illustrates this type of behavior. We're a very simple example. We could have worked this out in 1965. We look at the dependence of second harmonic generation on the linear dielectric permittivity. So these are just the standard equations for second harmonic generation. Here we plot the second harmonic intensity as a function of propagation distance through a chi2 medium. If epsilon is equal to 1, we get this curve. If epsilon becomes 0.1, we get this curve. 0.01, we get this curve. So you see that the distance over which the second harmonic term builds up becomes much shorter as we gradually decrease the dielectric permittivity. Okay, next topic that I wanted to talk about is a metasurface. So we took our indium tin oxide and we created a metasurface. We did so by depositing an array of gold nano antennas on top of the indium tin oxide, which was sitting on glass. And here is a micrograph image of what we had for our work. Now, what we found is that this structure had an even larger nonlinear response than the ITO itself. And then the question is why? Well, there's a lightning rod effect that these antennas channel the electric field of the incident radiation into the indium tin oxide. There's another effect, which I call the coupled resonator effect. There's a ENZ resonance and there's a nano antenna resonance, and we put them on top of one another. So first of all, just to tell you what I mean by the ENZ resonance, this shows a dispersion relation for indium tin oxide. Here is the frequency. Here's the wave vector. First of all, just to calibrate ourselves, the light line for vacuum would be this. The light line for BK7 glass would be this. And you see that there are two pronounced modes that occur. This one here is sometimes called the long range SPP mode, or the ENZ mode, or the bulk plasma mode. This is the short range surface plasmon polariton mode. In our work, we were exploiting this resonance, not this resonance. So here's what we found. Here is the results expressed as an N2 type nonlinear response as a function of wavelength. This is just for one particular antenna length. By changing the length of the antennas, we can change the resonance structure. But in this case here, we found that the N2, first of all, became negative, then it crosses zero here, and then it becomes positive. So first of all, this is a very, very big value, 20 million times the N2 of silicon dioxide. Sorry about that, it was my telephone. So what do we see here? That N2 can be either made to be either negative or positive. It has a very large value. And by changing the length of the antennas, we can control where this zero crossing is going to occur. Okay, now materials for epsilon near zero. And I'm short on time, so I'm just going to go quickly through it. First of all, my group is not the only people who thinks that this is important. So here's just a brief summary of material systems that people have used to study near zero index effects in photonics. Now, here's some of my own work. We measured the nonlinear optical properties of a layered metamaterial in its ENZ region. Now, the reason why this is important is that this is a metamaterial. So the question is, can we understand the resonances of a metamaterial in terms of the effective refractive index and the effective epsilon of its constituent components? So here's what we're considering: alternating layers of metal and dielectric. We change the amount of metal in the composite, and in doing so, we can land on any one of these curves. This means that we can set the epsilon near 0 point anywhere in the range of like 350 nanometers to 700 nanometers. So we constructed one of these by deposition, and we measured the real and the imaginary parts of epsilon. We find that the real part of epsilon vanishes at the wavelength of 508 nanometers. We do Z-scan, and well, you can just see by eye. If you don't do Z-scan, don't worry. This is a measure of the nonlinear response. For our composite, we get this curve here. For pure silver, we get this curve here. And even though there was for pure silver, we have this curve here. And you see that the composite material has a much, much larger response than pure silver would on its own. Okay, and last, applications of ENZ materials. And I'm afraid I have time for only one of them. So I will do this one here because I particularly like it. I think we all remember Princess Leia, or a hologram of Princess Leia asking Obi-Wan Kenobi for help. But the point I want to make is that with technology of today, 2021, we do not have the technology to update holograms at a video rate. We just don't have it. So our goal is to do real-time holography with video or much faster refresh rates. ITO has refresh rates that permit terahertz rates. Important applications includes image processing and signal processing. So we did the experiment. Here's a signal beam, which happened to be a petal beam from OAM studies. The signal beam and a reference beam interfere. They write a temporary grading, dynamic grading of the material. Then the readout beam comes later, but by as much as a couple of picoseconds. This diffracts off the hologram, and we get the transmitted readout beam plus the reconstructed beam and the conjugate. And here's data showing this down here. And we are interested in publishing this very soon. Now, I've run out of time. The next topic was going to be next topic is time refraction and how it's related to usual spatial refraction. So here's past work in the field. In this past work, which certainly was compelling, they had a change of refractive index of 1 part in 10 to the 4th. So they were not able to get a very large shift in frequency. But with an ENZ material, we can obtain a much larger delta N, and therefore a much larger change in frequency. So here is our setup. This is also known as adiabatic wavelength conversion. The output of an parametric amplifier is broken into a pump beam and a probe beam. A delay line can change the relative time that the pump beam arrives at the sample. Sample is here, and we just measure the transmitted light with an optical spectrum analyzer. And here are the results. Experiment and simulation are in very good agreement. This is the frequency shift that we can impress upon the beam as a function of the delay time between the signal beam and the pump beam. So we can control this delay. We can control it over as much as 75 nanometers of wavelength. And the application we have in mind, just one of them, is wavelength division multiplexing for telecom. So we have some new results as well. I can't talk to you about that. And just the very last thing, which we're working on right now in the laboratory, is ultra strong coupling of surface plasmon polaritons and epsilon near zero modes in a gold ITO bilayer. So here's our sample: gold on top of ITO on top of glass. Okay, so first of all, what are
Bob, I hate to say, but we are at the limit. We are past 3 minutes. Past 3 minutes, and I want to have some questions.
Sure. Okay, so I'm done, and thank you, everybody.
Okay, thank you for a very exciting talk. So I encourage you to ask some questions, maybe 2 or 3 questions. I would recommend, unless you want to speak up, to put them in the question answer. In fact, Bob, you should be able to see the Q&A. Otherwise, I'll read it for you. In fact, I can read it. Thanks for the inspiring talk. 2 quick questions. So you mentioned that the N2 goes with the root of epsilon over mu. Does that mean you do not want EM and Z material for boosting the nonlinear response? First question. And then second, the homogenized picture does of course not consider the huge changes in the density of states in the metamaterial. Can you comment on the implication of a more accurate theory? Maybe you want to compactify your answer because it's a long question, so we can allow a second question.
Sure. The first question was?
The N2 goes with the root
Right, okay.
of epsilon over mu. Does that mean you do not want EM and Z materials for boosting the nonlinear response?
Let's see. I've looked into this and I forget the details, but there's a sweet spot. You want epsilon and mu both to go to 0, but not necessarily at the same rate. That's the first comment. Second comment is that in reality, any material that we've studied so far, I mean the entire community, the imaginary part of epsilon is large enough that this effect does not show up in the laboratory. It's a conceptual point that we were working on, at least at this stage. And a more accurate model involving the density of states. Yeah, I don't know how I've gotten this far without talking about density of states, but I have. In fact, in the talk is given today, the density of states didn't appear explicitly. That comes into play when we are modeling the nonlinear response. And I have to go back and look at my notes and see what we've done. We certainly know about that effect.
Okay. Bob, last question, because we really have to move on since we are starting to get a bit late. And the next one is actually a very good one. Can you talk a bit about the ultra strong coupling regime?
Okay, so this was Nader and Gaeta's idea. Oh no, the ultra strong coupling.
Yeah.
Yeah, I mean, I guess those words apply to 2 different things I talked about. So, so I ran out of time here. You have the ENZ mode and the surface plasma polariton mode. They couple to one another to form polaritons. Here's the upper polariton, here's the lower polariton. In our laboratory work, we just now got an infrared spectrometer. So we have data for this polariton, but not for this polariton. And the experiment and the numerical simulations agree very well with one another. Okay. Whether it's strong or ultra strong is a semantic point. And we're defining it to be ultra strong coupling if it's just arbitrarily above this line here. Okay. So good. Strong coupling.
Maybe if I may say, thanks again, but we really have to move on. Thank you so much, Bob. So folks, let me introduce